Hi, welcome to Excellent Grades Academy. This is Dr. Byson EM. In this video, we're going to look at Organic Chemistry Tutorial Sheet 4 from the University of Zambia. Now remember, question 1 of this tutorial sheet has already been solved and the video is already there. You can check it in the playlist. We're going to start from question 2. Question 2 says, give structures for compounds A to E in the synthetic scheme below. So they did not necessarily require mechanisms for this, but I'm going to provide some mechanisms that I feel are very important for you to know in organic chemistry. Okay, so let's start. Okay, so they're saying cyclohexanol. So this is our structure for cyclohexanol here. Cyclohexanol is reacted with potassium dichromate. When you react an alcohol with potassium dichromate, what you are doing is you are oxidizing it. Okay? You are oxidizing it. So oxidation is simply the loss of hydrogen. So this hydrogen here is going to be lost. And then this single bond, this is a hack that you just have to know. This single bond is going to be converted into a double bond. So the structure that you will form is this structure here. So that is the structure that you're going to form if you expose cyclohexanol to potassium dichromate. So this is our structure A here. And then this cyclohexanol was treated with a Grignard reagent. So this Grignard reagent is CH3MgBr. Now we know that the Grignard reagent, the carbon that is attached to the Mg, to the magnesium, is negatively charged and the magnesium is positively charged. So this carbon is going to come and attack this carbonyl carbon here, and this bond is going to break. What you're going to have there is that the methyl group is going to join at the carbonyl carbon. So you have a structure like this. Okay. So this oxygen here got the electrons. So it will be negatively charged and the methyl will attach there. Now remember, we also have an acid in solution. So this acid will produce a hydrogen ion that the negatively charged oxygen is going to get. So what you're going to produce at the end of it all is this compound there. Okay, so just give me a minute. So this compound here is what you're going to produce. So there will be an OH here and a methyl. So this here is compound B. That is compound B. Then this compound B is going to be treated with an acid. So HA is simply an acid. And at very high temperatures. So that's why they have indicated heat there. Now what is going to happen is that, let's move on to the next page. This compound that was formed, okay, so let's put it here, and then there was a methyl there. This was treated with an acid there. This hydrogen, this oxygen will get the hydrogen from the acid, and this is going to break. And what you're going to have is a protonation of the oxygen ion there. So since oxygen is attached to three things, it is going to be positively charged. This A got the electron, so it will be negatively charged in solution. This will undergo an elimination reaction. So this A will get this hydrogen, these electrons will fall there, and then this will be a good leaving group, so it's going to leave. So now the compound that you form is this one here. Okay, so this compound that is formed now is C. So that is C. Then C is going to be treated with ozone that is put in dimethyl sulfide. So this reaction is called ozonolysis, and we know ozonolysis is simply oxidative cleavage. So let's see how ozonolysis is going to take place. There's a very short form on how to predict products from ozonolysis. So if you treat an alkene in ozone and in dimethyl sulfide, what you're going to do is that, let me use another color here. What you're going to do is that you're going to cleave this double bond. You're going to cut it in half like that. If you cut it in half, then what you form is this. So there. So this will be a double bond, and this will be double bond. But here you're going to add an oxygen after you cut. And then you're just going to straighten this. So if this was carbon number 1, number 2, number 3, number 4, number 5, number 6, number 7, you're going to start. Okay. So carbon number 1, number 2, number 3, number 4, number 5, number 6, number 7. Carbon number 2 is double bonded to oxygen, and carbon number 7 is double bonded to oxygen. 1, 2, 3, 4, 5, 6, 7. But you know that carbon number 7 here has a hydrogen. So this is the compound that is going to form when you treat this alkene with ozone. So this is our D here. That is our D. All right. So that is our D. So this has moved. That is our D. So this is our D. Okay, so pardon me. This has moved, but it's all right. So our D would then be treated with diamine. Let's look at this compound. It will be treated with this silver diamine hydroxide. If you treat an aldehyde with silver diamine hydroxide, this is called the Tollin's test. It is going to convert the aldehyde to the corresponding carboxylic acid. So what you're going to do here, okay, it's back now. So if you treat, all right, so if you treat if you treat an aldehyde, you know this is an aldehyde here, you treat it with diamine silver hydroxide, which is a Tollin's reagent. What you're going to get is that this aldehyde here will be converted to a carboxylic acid. So you're going to add an oxygen here. So you're going to have 1, 2, 3, 4, 5, 6, 7. Here there's a double bond. Here oxygen. So you've converted this group here that was an aldehyde to a carboxylic acid there. So that is how question 1 is going to react. Those are some of the reaction mechanisms from question 2 rather. And those are the products that we predict. So this is E here. And then this is D. This was C. And this was B. And A, we already showed A. A was here. Okay. Question 3. Let's look at question 3. So question 3 says a compound of formula C5H10 and an oxygen gives a positive Brady's reagent. So now Brady's reagent will be positive. Positive simply means that there's a carbonyl group in your compound. There's a carbonyl group. A carbonyl group is simply a carbon double bonded to an oxygen. That is Brady's reagent. That is what they're telling us. So in this compound here, they're saying there is a carbonyl group. Number 2, they're saying that it gave a negative reaction for the Fehler's test. So the Fehler's test or the Fehler's solution test, Fehler's reaction is negative. So let's start, is negative when there is a ketone, but is positive when there is an aldehyde. So we know that this one here is negative. We know that this compound that they've given us is a ketone and it is not an aldehyde. And then what they're telling us is that it gave a yellow precipitate when treated with 10% iodide or potassium iodine. 10% iodine or potassium iodide and sodium hydroxide. That is called the iodoform test. So the iodoform test is positive when there is a methyl ketone. So there is a methyl ketone where the carbonyl carbon has got a terminal methyl group. Okay. So now they're saying draw the structures of all the components of all the compounds that would give such results. So we know that our compound has got 5 carbons. So we draw it 1, 2, 3, 4, 5. And it is a ketone. So we're going to put the oxygen here. So this number 1 is a ketone. The Brady's test is positive. The Fehler's test is negative. And there is a terminal alkyl group, methyl group here. So this is a possible structure. Second one, it could be this. 1, 2, 3, 4. Could be this. We know it is a ketone and it has a terminal methyl there. So these are the 2 possible structures that can exist. So these are the 2 possible structures for this question. Number 4, an isomer of the above compound gave a yellow precipitate. So they're telling us again that the Brady's test is positive. So they're saying positive Brady's. So meaning there is a carbonyl compound in this carbonyl group in this compound. We've established that. And they're telling us that there's a red precipitate with a Fehling solution. So positive Fehlings. We now know that this is an aldehyde. Why is it an aldehyde? Because the Fehling's test is positive and there is no reaction. So they're telling us that there is a negative iodoform test. So meaning that there is no terminal methyl group. No terminal methyl. So they're telling us draw the structures of all the isomers. So in order to draw the structures, the first one would be 1, 2, 3, 4, 5. So this is an aldehyde and it has 5 carbons. Second one would be this guy. 1, 2, 3, 4. 1, 2, 3, 4. To be this. So these are the possible structures. These are the possible structures for for this question. All right. Question 5 says acids F and G have pKa values 4.2. So the pKa values, so pKa for F is 4.2, and then the pKa for G is negative 3.3, and they're asking us which acid is more acidic. So we know that the lower the pKa, the stronger the acid. The lower the pKa, the stronger the acid. What this simply means is that G will be a stronger acid. So here G is the stronger acid. So that is 1. 2 says upon reaction with a base, which of these two acids would form a salt with a pH less than 7? Okay. So here the weaker the acid, the stronger the conjugate base. So meaning that F, which is the weaker acid, will form the stronger conjugate base. So F here is the answer. F will form stronger conjugate base. All right, let's move on to question 6. So question 6 says between phosphoramine, which is pH 3, and ammonia, which one would you expect to be a stronger acid? Explain. Okay, so question 6. Let's solve this. So which one would you expect to be the stronger acid? Between pH 3 and keeps on doing this, and NH3. So the answer here is pH 3. Why? Because number 1, phosphorus will form a more stable negative charge than hydrogen, and phosphorus has got a less grip to its H ions compared to hydrogen. So pH 3 would be a stronger acid compared to NH3. Question 7. When the following compounds are mixed, an acid-base reaction is expected. Predict the products of such a reaction in each case. So here you've got pH 3 plus H2S. So here the base is going to be this, and this will be the acid. Why? Because sulfur is more acidic than phosphorus. So sulfur will be more acidic than P. So it's the compound that has got sulfur in it will be more acidic than the compound that has got phosphorus in it. So since pH 3 is the base, it is going to obtain 1 proton from sulfur and to be positively charged, and this will lose 1 proton, so it will be negatively charged. This is how it is going to be. Number 2, pH 3 plus water. So here you ask, which one will be the base, which one will be the acid? We're going to determine this using the pKa values. So we've seen that the pKa of water is less than the pKa of pH 3, meaning that water will be the acid. We said that the lower the pKa, the stronger the acid. This one will be the base. So since this is the base, it will get will be like this, positive, and the water will be the hydroxide, like that. So that is how that is going to work. That is the answer for this question, for question 6 and question 7. Question 10. In each of the following organic compounds, 2 hydrogen ions are explicitly shown. Draw the conjugate base corresponding to the deprotonation of each. Okay. So if you deprotonate, so there's a hydrogen here and there's a hydrogen here. If you deprotonate this hydrogen here, what you're going to have in question 1 is that you're going to have this compound. Okay, so the compound is like this. If you deprotonate it, it will remain like this. So this will be conjugate base 1 to be negatively charged here. This is still intact. So this is conjugate base 1. And then conjugate base 2 will be where this hydrogen here is deprotonated. So conjugate base 2 will be negatively charged. So that will be conjugate base 2. Like this. Now they're asking which hydrogen is more acidic between this hydrogen here and this hydrogen here. So the hydrogen that is more acidic is this one here. More acidic. Why? Because this hydrogen is attached to the oxygen that is attached to a double bond, a pool of double bonds. So that's why it is more acidic. Okay, let's move on to another question. It says number 2. So you have this compound here. Let me try to draw it here. So with the hydrogen here that is attached to the oxygen, and then the oxygen is attached to that. Nitrogen is here. Okay. Okay, like that. So there's a nitrogen here. So now the question is the conjugate base. The first conjugate base is where you lose this hydrogen here. So you're going to have the oxygen lose the hydrogen, so it will be negatively charged. And then the nitrogen will still have. And then the other conjugate base is where the nitrogen will lose the hydrogen. Okay, so the oxygen can either still have it like this, so conjugate 1, conjugate 2. Now question is, which hydrogen is more acidic between hydrogen A and hydrogen B here? So the hydrogen that is more acidic is this hydrogen. More acidic. Why? Because the oxygen, this hydrogen is attached to the oxygen, and the oxygen is more acidic than the nitrogen. All right. Let's go to question 3. So let's do it from here, because this is where the questions are. Okay. So question 3. So the conjugate is where, first of all, you lose this one, you write the conjugate, and then you lose this one, then you write the conjugate. So it's going to be like this. So the first conjugate is where you lose the hydrogen that is attached to the oxygen there. Then you have this. So because the oxygen has lost the hydrogen to be negatively charged. To be negatively charged here. So this is conjugate 1. Conjugate 2 is where you lose the H that is attached to the sulfur. So this will be conjugate 2. So conjugate 1 is like this. Conjugate 2 will be like that. So now they're asking, which one is more acidic? This one, like this hydrogen, or this hydrogen here? So the more acidic hydrogen is the one that is attached to sulfur. So here what you have to know is that although oxygen is more acidic than sulfur, sulfur is more acidic than oxygen because of its size. So sulfur forms a more stable negative charge than oxygen. That's why the hydrogen that is attached to sulfur is more acidic. Okay. So that is the answer for question 3. 10.3. Question 10.4. So first of all, they're asking us to draw the conjugates. Conjugates are formed when an acid loses a proton, it loses a hydrogen. So you form a conjugate acid, conjugate base. So the structure is this one here. If this structure, this nitrogen loses a proton, it loses this hydrogen here, it's going to be like this. So this one still has its H. This one has lost, so it will be negatively charged there. So this is conjugate 1. Conjugate 2 is going to be, so this one had already lost. This one will now lose, so it will be negative. All right. So now we're asking, which one is more acidic? Which one is more acidic between this hydrogen there and this hydrogen here? So the one that is more acidic is this one here. Why? Because they're both attached to nitrogen. So what makes this hydrogen more acidic than the other one? It is because this nitrogen is attached to 2 carbons that are both double bonded to the oxygen, while this one is only attached to 1 carbon that is double bonded to oxygen. So there is a rich electron pool here attached to this nitrogen than this one here. That's why. Okay, let's move on and go to question 10. Question 11. So question 11 says Orlistat is an anti-obesity drug which inhibits pancreatic lipase. Pancreatic lipase is simply an enzyme that is produced from the pancreas that digests fats. So Orlistat is a drug which will inhibit pancreatic lipase, blocking the enzyme from digesting fats in the intestines. This results in less absorption of fatty acids and glycerol. Orlistat forms a permanent covalent bond with the enzyme. So the first step in the reaction involves nucleophilic addition to the carbonyl-carbon of the four-membered ring. The second step forms one of the two intermediates, which is H and I. Okay. So let's look at what they're asking us here. So this is H and then this is I. Which of the two intermediates would be formed or favored? So if you look at H here, you find that the intermediate has got a negative charge that is formed on oxygen. Here on oxygen. Like that. And then in I, the negative charge is formed on carbon here. So now the intermediate that will be favored is intermediate H. So the answer is intermediate H. Why would it be favored? Because oxygen forms a stable negative charge compared to carbon. So that's why intermediate H is formed. Why? Because the negative charge is formed on the oxygen here compared to this one that is formed on the carbon. So intermediate H will be favored compared to intermediate I. Question 11 was very easy. It looked intimidating, but it was easy. Okay. 12. Which acid of each pair shown below would you expect to be stronger? Explain. So in 1, I would expect this acid to be stronger. Why? Because it has a halogen here that is attached to this carbon, the beta carbon, while this one doesn't have a halogen. Number 2, between these two, which one will be stronger? This will be stronger. Why? Because the halogen here is fluorine and the halogen here is chlorine. Fluorine is more electronegative than chlorine. So that's why that will be stronger. And then between this one and this one, this one and this one, this will be stronger. Why? Because the fluorine is attached closer to the carbonyl-carbon, whilst here it is further. And then in the last one, which one will be stronger? This will be stronger. Why? Because this one here has got a halogen, whilst this one doesn't have a halogen. So this group here is C3F, whilst this group here is just CH3. This is more electronegative than this. That's why this acid is stronger. All right. Question 13. This is more interesting. Says an unknown compound A, which is C5H10. This is an alkene. Why? Because the number of hydrogen atoms are just 2 times, exactly 2 times compared to the number of carbons. So unknown compound A rapidly decolorizes a solution of bromine. So if I was to draw this alkene, it would be like this: 1, 2, 3, 4, 5. This is alkene. And if I reacted it with bromine in carbon tetrachloride, it will react like this. And then 1, 2, 3, 4. It is going to react like this. There will be a positive charge here, and then there will be a bromine in solution. This will come and react here, and it will give me this. So it is going to break down bromine. That's why it will decaralize bromine. And then they're saying when A, this is A here, is dissolved in concentrated sulfuric acid and heated with water, B is formed. So when we react this guy here, which is an alkene, 1, 2, 3, 4, 5. So this is just pentene. Pent 1 in. You react this with sulfuric acid. You know sulfuric acid is like this. And you put it in water. What is going to happen is that this double bond will get this proton from the acid, and then it will form this compound. So the hydrogen will be added here. And then there will be a positive charge here. And then the water in solution, like that, will come and attack there. So it will be like this. Positively charged. And then this one that was in solution will come and get the hydrogen. So you form this compound. You form an alcohol. So this alcohol here is the B that they're talking about in solution. This one. It has 5 carbons. 1, 2, 3, 4, 5. And then it has 12 hydrogens. Here there are 3, 2, 2, 3, 10. Here there is 1. Here there is 1, 12. So that is B. And then this alcohol will react with chromic acid. Now you remember what we said, that when you react an alcohol with chromic acid, what is going to form is a ketone. Okay. So this alcohol that is formed here, 1, 2, 3, 4, 5, it was formed here. When you react it with chromic acid, what you're going to form is that you're going to lose this hydrogen here. 1, 2, 3, 4, 5. And then you form a ketone. So this is the ketone. So this ketone that is formed is C here. That is C there. So this is compound C. This is compound C. And what they are saying is that both B and C give positive iodoform tests. Each iodoform reaction mixtures contains, in addition to CHI3, an anion of butyric acid. What is the structures A, B, and C? So we've already talked about the structures. Okay, so A is this one here. And then we formed B here. And then for C, this is C. That is C. So it was a very simple question. Let's move on. So 14 says compound A does not give a product with phenyl hydroalazine. Phenyl hydroalazine is simply Tolin's test. Oxidation of A with potassium dichromate gives B, and compound B reacts readily with phenyl hydroalazine but does not give the Tolin's test. So the original compound A can be dehydrated with sulfuric acid to give a hydrocarbon, which is this one. Ozonolysis of the hydrocarbon C gives an acetone and an aldehyde. Now deduce the structures A, B, and C. So A says it has a compound formula of C5H12O. So we know that this is an alcohol. So this is carbon number 1, number 2, number 3, number 4. Okay. So this alcohol here is going to be like this. 1, 1, 2, 3, 4, 5. And then when you react this, they're saying compound A. So this is compound A. It's going to be oxidized by potassium dichromate. Remember what we said about oxidation? The H is going to go, and then there's going to be a double bond between the carbon and the oxygen. So it will form this. So this is compound B. Compound B reacts readily with phenyl hydroalazine but does not give a toluene's taste. Okay, so meaning that this is a ketone and it is not an aldehyde. That's why it does not give a toluene's taste positive. Then this compound they're saying that compound A can be dehydrated with sulfuric acid to give the hydrocarbon this. So C5H10, which is a ketone. So when we get compound A, and then we dehydrate it with sulfuric acid, what we're going to have is an alkene, like this. Because you know that when you react an alcohol with concentrated sulfuric acid, what you are going to have is turning that conversion of that alcohol into an alkene. So this is compound C. And then they're saying ozonolysis of compound C will give an acetaldehyde. So if you ozonolize, you will react C with ozone in dimethyl. So react this C in ozone and dimethyl sulfide. What you're going to have is that you're going to have cleavage of this double bond. And then when you cleave that double bond, you're going to have this plus. So this is acetone. And then this is an acetaldehyde. Acetaldehyde. So that is how this reaction is going to be. So this is A, this is B, this is C, and then when you oxidatively cleave it using ozone and dimethyl sulfide, you're going to get acetone and acetaldehyde. Okay. Question 5. How would you distinguish between, question 15, how do you distinguish between 2-pentanone, which is 1, 2, 3, 4, 5 here, and 3-pentanone, which is 1, 2, 3, 4, 5. They're both ketones. So how would you distinguish between these? The answer is very simple. 2-pentanone has got a terminal methyl here. So meaning that it will give a positive iodoform test. Iodoform test. So when you react it with iodine in sodium hydroxide, it will give a positive iodoform test. This one doesn't have a terminal methyl, so this one will give a negative iodoform test. That's how you differentiate them. It's very easy. The last but not the least, how you distinguish between propanone. Propanone is this. And ethyl. Ethanol. So ethanol is like this. So you know this is a ketone. This is an aldehyde. How you differentiate them is that the Tollens test, you differentiate them using the Tollens test. So if this is A, this is B. The Tollens test for A will be positive. But the Fehling's test, for A would also be positive. But then for B, the Tollens test for B will be negative. Because it is an aldehyde, Tollens tests are only positive for ketones. But the Fehling's test, will be positive. That's the way it is. Okay. So here, what you need to understand is that for B, the Fehling's test, for A, the Tollens test is positive, but the Fehling's test is negative. It's negative rather, because it is a ketone. But then it will be in opposite. So the Fehling's test will be the major difference. Fehling's test for A will be negative. Fehling's test for B will be positive. Okay. That's how it is going to be. That is how it is going to be. So comment down below and then practice, and then I'll see you in the next video. All right.